So let's see if this will let me sign in today. Hey, how about that? Okay. So first things first, we have a video of our student Alan Sargent who is testing his bridge here. So we're going to go ahead and take a look at that, and we have two bridges here in class to look at as well. So we'll look at those, and then we will discuss what will be happening next week. Before we start watching these videos, remember that there is still the paperwork on the bridge that I would like turned in. If you haven't finished it yet, please finish it by Monday, get that turned in to me. All of the design work, all of the evaluations of your different designs, and then of course your evaluation of your final design. And as far as the video is concerned, I will be taking video of the testing today, so you won't need to do a video if you're testing in class. I will have that. But everything else, get done, get turned in, and we will be starting some new stuff Monday.
I think this is rolling. Here's my bridge, my two tables, which I have. Right. Starting height of at the bottom here. Excuse me.
Flip that over.
30 and 1/16. Dumbbell from the weight room, which I will now test. Maybe.
Pull it back in.
It's just a string suspended from the middle.
Such straight. Did he use string on it?
Yeah.
Impressed. That looked really nice.
I have more aesthetics than mine, but
Yeah, string.
Again, would be almost exactly 30 inches tall. Just maybe even a little shorter, 29, and it's pretty close to 30 actually. So there it is.
So it looks like about a 3/16 inch deflection on that bridge. And let's go ahead and let's go back to our PC, I guess. guess we're on piece here. Okay, so that is our first test. Looks like a good one. So who wants to go next?
I'm down.
Okay. Let's go ahead and measure here.
Yeah.
Just sure.
I had to shorten that up a bit.
Hold on
Yeah,
a second,
so
let me see if this is actually 24. It's actually a little bit, can't tell what that is actually.
it'd be close because I made it so it just had a little bit left over to.
These tables are kind of goofy because they have this rounded edge.
Yeah.
So I'm going to go from the rounded edge to the rounded edge.
Okay.
So go ahead. It's close. Okay, it might stay there. It might stick
Yeah, it's a bit warped too, so that's not helping.
Well, let's get something to hang these weights with. I'll put them on there. You want to measure the height of your fridge?
28 and 15/16. Well, yes, this is an 8. 7/8. That'll be easier.
28 and 15/16, you say?
But I'll just go with 8s since
Okay.
it's by 8s. It was really close.
Okay. And we'll try to put this in here so it gives a nice. Distribution in the middle here. Okay. I'm doubling it up this time since last time I broke a string. Try to make it a little bit stronger this time. Okay. Now we're going to start off with just about 5 pounds, just to kind of see where things are at so we don't break things right away. Doesn't look like there's going to be any trouble holding this.
I hope not.
Okay, that's about 5 pounds, 4.5. Let's go up to 10 and then 20 and see where we're at. So what was your original height, did you say?
The original height, 29 and 7/8.
29 and 7/8, okay. So that's about 10 pounds on there. You want to measure that and see where we're at?
On that, so it's about, did I say 29 last time I told you?
Yes.
28, I'm sorry.
28 and 7/8?
Yeah, so now it's about 28 and,
1/16 less or so?
Yeah. Just a little bit of deflection.
Okay, so about a 16th with 10 pounds.
It's just
Broke a little piece there.
I'll hold it right.
And we broke a string here too.
Oh, okay.
Wouldn't you know it? Let's see if I can fix that real quick. Do a little Boy Scout square knot here. Need to get some better string for this. Probably just some rope will do.
Yeah.
Just what I had available at the moment. So putting this on, let's see, each one of these is 5 kilograms, so this is actually a little over 20 pounds. And the string breaks before the bridge does.
Yeah, I thought the bridge was going there,
No,
so.
it's the string. You can hear it.
Yeah.
All right, good job.
Awesome.
I'm not sure if the video saw it because we were still on.
I thought about that too.
So what did we see? Did you see another deflection of about a 16?
Yeah, so probably grand total of about 2/8. So even
Okay.
a quarter of an inch.
You want to bring yours over here?
Sure.
Let's get some new string out.
It did warp a little bit.
That happens. So with the I-beams, last year I didn't have any students that used I-beams, and I really only had one student that did very well at this last year. With the I-beams this year, all the students are doing well. I'm wondering if I should maybe disallow I-beams. It just makes it too easy.
No one suggested that.
Well, I know. I did it on purpose because they're a good engineering. There's no doubt that they're
Absolutely.
great for engineering. Let's reuse this piece here. I don't even know where I got this stuff from. This stuff is like twine from the 1800s. I figured I might as well use it up instead of spending more money. Public schools like this, money spent is taxes spent. Okay. So what I'm going to do here is I'm going to quadruped up now, even stronger. We've already done yours. We've already weighed yours through.
Well, it kind of changed.
A little bit different design you've got going on here, right? Not that much different.
The same materials.
So, measure height.
Yeah.
What was it?
29 and
29 and 16. So what's it at now?
Still at 29 and 16.
What did you do?
Didn't change.
So we got less than a 16th deflection. Okay, good. All right. Well, we are doing well then. We have 3 bridges. They all pass inspection for doing the job they needed to do. And now it's your job to figure out the efficiency of your bridge, which essentially would be the amount of materials that you use to get the job done and how well it adheres to your design and how good it looks and all that stuff. So we're done with our first major project of the semester, and we can move on and start moving a little quicker now that we've got that first one kind of out of the way.
I think this is rolling.
So, this here. And let's go back to our syllabus and see where we're at. We're obviously not going to be quite on the schedule that we originally started with, but let's go check it out anyway. Let's see. What we're going to do right now is we're going to update our syllabus with kind of a slightly new schedule since we're off a little bit, and then we will move on with that schedule in the future. So here's our bridge project, and it was originally scheduled to end the 17th, and this is the 24th, is that right? So we're about a week out. So what we're going to do is we're just going to move some things down here. This project will take a little bit less time with probably because we've got some experience now. We'll move all these down. And so we've got now 3.6 that we will actually, let's see, let's move them down one more level here. Okay, so, wait, is today the 24th? No, today's the 26th. So Monday's the 29th. Okay, so that's right. I got that right. Okay, so the 26th was, we go to chapter 3.6, and then chapter 5, starting next week, we will do chapter 5. Also remember, if you haven't turned in your homework for chapters 1 and 2, let's get those in. I'm in the process of getting those graded and starting up some grades for this class so that we can have something to base your grade on besides just projects. We only do homework for these few chapters, just the 1, 2, just one problem in chapter 3, and then 5 and 6. So we've only got a few homework assignments and then all these projects that we're going to be doing. Let's take a look at our grading scale. I can't remember all how our grading scale works. We have our quizzes, 10%, homework 25%, exams 30, project reports 25, and professionalism at 10%. We haven't scheduled any exams yet, but we will certainly do that after we're done with our bookwork. We'll do an exam on that stuff. So that'll be sometime in October here. And we're going to push probably chapter 6 off probably about a week, or at least a couple of days, because we want to give ourselves at least one more day on this problem-solving project for the rubber band-driven car. So what I'm going to do is I'm going to cut this out, and we're going to maybe cut that out. Give ourselves an extra day, give ourselves just one extra day in here. Oops, that's not what I want to do. There we go. So now we're going to have enough time. Okay, so what we've got so far is we're going to get into chapter 3 today a little bit. Do chapter 5 next week, so mostly bookwork next week, some exploring of stuff online together, and a little bit of discussion of topics in chapter 5, and then we'll move down into October here in the second week of October, I guess, and we'll do another project, our rubber band driven car, and that project is different than you might think. We're actually going to do it for the slowest speed over a distance. So you'll have essentially, you'll have to make a car that moves very, very slowly, but for a particular distance. It has to reach a particular distance in the slowest amount of time possible. Okay? And that distance will not be the distance the car moves, it will be a distance along the ground. So it's usually what we will do in this particular project is you will have essentially a 1 meter radius circle. So you'll be inside of a circle that is 2 meters across, a 1 meter radius circle, and your car will be in the middle of the circle, and whenever your car leaves the circle is when we count your times. You start the time when your car begins the challenge, and then we end the time when it leaves the circle. And so that's your project. Or we end the time when your car stops moving. And if it stops moving, if it stops moving before it leaves the circle, you also get penalized. So that's part of the thing that you really want it to both leave the circle and be in the circle as long as possible. It's kind of a different challenge, and most of my students that did this last year didn't get more than a couple of seconds. It was very difficult for them to design this car so that it was in the circle for very long. I actually did a square last year. This year I'm going to do a circle. See how it changes. I also did a 1 meter square last year, and this year I'm going to do a 2 meter diameter circle. So it'll be almost 4 times as big this time, about 3 times as big this time of an area. So anyway, that's our next project, and we'll jump into Chapter 6 after that just for a couple of days. And then we'll jump into the trebuchet project. Notice that this problem-solving project up here and the trebuchet project are actually are done differently in the syllabus. In the problem-solving project, I'm just giving you this week to work on this stuff. You'll have a workbook to do, very similar to the one we used this time. But then in the trebuchet project, we have certain days that are set apart for certain things. In the first one, we have the trebuchet project is define, identify, search. The second one is feasibility, preliminary, detail. The third day is construct, and the fourth day is to verify. So this is the first time here with the trebuchet project that we're going to be following kind of the design method of engineering on our own without some predetermined workbook to work from. So we're going to use specific days for you to follow through the design process of engineering on your own. You're going to be working out your own notes and your own workbook essentially. You'll be going through the process without somebody holding your hand or guiding you through it. And we have a schedule to follow in that as well. Then we move on to the motor project, which we will follow very similar protocols as this one. Then the radio project, and then our final big project of the semester, which happens right before Thanksgiving, which is the hydraulic arm project. And that's easily the most complex project of this course, where you're going to build a hydraulic arm that is designed to move, pick something up, rotate it around, put it somewhere else, and all through hydraulics. At that point, we have our holiday, of course, and we get on to some three-dimensional design. You guys are going to learn a little bit of how to do three-dimensional design and do some 3D printing with our 3D printer. Get to end the class on a fun project. And that particular project has to do with designing and printing buildings for the city of North Platte. We're going to build a three-dimensional map of the city of North Platte. We're going to start today. So, we started last year, we'll do some more of it this year. So, I will email this to you all. Let's see if I can, maybe I can email it from here. It's new email. Apparently it doesn't know who you guys are. Let's find you guys in my address book. Engineering. It's not here. Dirty dog. Okay. So it doesn't know how to do that on this computer. I will just send myself an email to remind myself. Okay. So anyway, that will be forthcoming, and let's go ahead and get started. Let's go ahead and look at chapter 3 in our book. I actually forgot my book, so I'm going to go grab it really quick. Or do I really need it actually? Which class am I in here? Let me go grab my book so I make sure I don't forget anything. I'll be right back, as you were. Okay, Chapter 3, Engineering Ethics. Why do we talk about engineering ethics in a class like this? Chapter 3.4 talks about the ethical engineer. The whole chapter is engineering ethics, really. They talk about etiquette, they talk about morals, they talk about moral issues, and ethical egoism, and the ethical engineer, rights analysis, resource allocation. They talk about all kinds of things, but in 3.6, they have a list of case studies of engineering things that we're going to go through today. Now, why do we have to have ethics as engineers? That's really the question. What are ethics, first of all?
Moral guide.
Moral guidelines, okay? Pretty much close, right? It's the set of moral values that you're going to follow. And engineers have to have specific moral values. Why?
You're in a very delicate situation, and if you have the possibility of screwing people over, doing stuff that's unethical and kind of getting away with it, or dealing with a whole lot of legal lawsuits.
Okay? So you could screw somebody over, have lawsuits. What else? What did we just build?
Bridges.
We built a bridge. Why do we have bridges?
To move people from one side of a gap to the other.
Yeah, from one side of some, like, danger, right? A river, a gorge, whatever. It's danger. That's the number one reason that engineers need to be ethical, is because of danger. It's not necessarily legal issues all the time, although those are always involved, but that's not really what we should be worried about as engineers. And it's not necessarily even taking advantage of people that we should always be worried about, even though that is part of it as well. The most important reason is safety, okay? The most important reason is safety in ethics when it comes to engineering. And so let's take a look at engineering ethics online. What do they have to say about engineering ethics online? It turns out that there is all kinds of things being said about engineering ethics online. There are institutes that give millions of dollars every year just to define the engineering ethics for the engineering fields. Sometimes there are engineering ethics in a particular field that are very specific to that field. Electrical engineers, for example, have a very specific set of ethics that they follow that are slightly different than maybe civil engineers. And if you just Google engineering ethics, the first thing that comes up is the National Society of Professional Engineers. Okay, this is something that you will be very familiar with if you go into engineering as a profession, because the PE, or Professional Engineer Society, is the society that not only certifies engineers but also regulates engineers. Okay? So if you want to go out there and work in the workplace and be a boss as an engineer, to be in charge of things as an engineer, to have responsibilities and to get a great paycheck as an engineer, even though you have maybe a master's degree or a bachelor's degree, you still have to go and take the PE exam. And the PE exam is a comprehensive exam. They can ask you any question that they want. There is no limit. They can ask you any question relevant to engineering, which means they can ask you any question in the world. Right? There's not much out there that they cannot ask you. I mean, they're not going to ask you anything about theoretical physics or anything like that. And they're not going to ask you anything about poetry. But they're going to ask you anything they want to about things that matter in everyday life of everyday people. The technologies, the infrastructures, the materials, these kinds of things. Now, if you're taking the PE exam for a specific field, for example, civil engineering, that test will be more geared towards civil engineering. It'll have a lot of things about materials that are used in building materials and so on and so forth. A lot of strengths, a lot of strength and force questions, water, questions about water flow and other things like that for civil engineering. If you're going in for electrical engineering, obviously, it'll be much more about circuits and electrical safety and things like that. But it is a major test, probably the most difficult test that any engineer takes in their career, education or otherwise. But once you've passed the test, and you can take it multiple times, once you have passed the test, then you get certification as a professional engineer, and all of a sudden your opportunities skyrocket. When my oldest brother passed the test, he went from being a junior, essentially technician, designing little widgets and things, or it's just tiny little parts of every project, to being one of the leaders in the company he was working for, to leaving that company for a job that paid twice as much and has lots more opportunities in a much better place of the country. And now he's very well paid, and has a great big house in Northern California. It's a very expensive place to live. And so he's doing very well. And it's in large part due to this, to getting certification from the National Society of Professional Engineers. Well, on the other end of the spectrum, not only certifying engineers, but they're checking up on engineers to make sure that they're doing what is right. So down here we have our Code of Ethics, the Board of Ethical Review. So they actually have a board of people that look at engineering messes, usually catastrophes, problems, screw-ups, and they decide whether or not the engineer was at fault or if it was some other thing. And they can come down, they can take away engineering certifications, they can reprimand, they can exact fines and other things like this. But what we're going to do here is we're going to look at the Code of Ethics, the NSPE Code of Ethics, and it reads very much like a constitution. It has a preamble, like our Constitution does, and then it has fundamental canons. Now, in the Constitution of the United States, the fundamental canons are essentially called the
Bill of Rights.
No, they're called the Articles. The Articles, I think they're called Articles. The Articles are essentially the kind of the building blocks of the laws of our nation. The Bill of Rights was not actually part of the Constitution was written. It was written later. And that is what the rules of practice are. So you have the preamble, which essentially says this is what this document is going to be all about. You have the canons, which say these are the 6 things that really make this document what it is. These are the 6 major points that we're trying to make in this document. And then you go on to the rules of practice where they take each one of those points and they elaborate on them a little bit, give you a little more detail. Okay? So the fundamental canons are kind of like the articles of the Constitution, and the rules of practice now are more like the Bill of Rights, where we're going to just give a little more detail. The Bill of Rights was intended to, it's an amendment to the Constitution. It's actually 10 amendments to the Constitution and then a few more, right? But the Bill of Rights was essentially just some clarification on some specific topics, right? That, in particular, the rights of the people of the country. And then they actually have at the end here professional obligations, which could also be considered kind of like the Bill of Rights in the Constitution, but might also be considered like the laws that are built from the Constitution. So it's just more of what the engineers should be doing to meet these obligations, or to meet these ethics, these rules of law, these rules of behavior in the engineering profession. So let's go ahead and let's just look at the canons really quick. Number 1, hold paramount the safety, health, and welfare of the public. So this is the number 1 thing, and for good reason. Hold paramount. What does it mean to hold something paramount?
To an extreme value?
Not extreme value.
To the highest.
The highest value. Paramount means the highest, literally. So if you hold something paramount, then it is the number 1 thing. It's not just important, it's not just really important, it is the most important, is the safety, health, and welfare of the public. Number 2 is to perform services only in the areas of their competence, right? This is a hard one for a lot of engineers. Why? Well, engineers are smart people. And smart people often have a tendency to think that because they're smart in one area, that makes them smart in all areas. Right? Anybody that's smart falls into that trap. In fact, some people that are just not so smart fall into that trap, unfortunately. But we need to exercise some humility. And it's important to understand where our level, where our expertise ends. And we have to be able to admit it to ourselves and to others very readily, and to not give advice or do designs or perform in any way, really, in an area of competence outside of our expertise. So number 3, to issue public statements only in an objective and truthful manner. Engineers are often put in a situation where they need to say something about engineering. Okay? If that is about engineering that you have done, or engineering that someone else has done, or engineering that's going to be done, then those things need to be said truthfully. It doesn't mean that you need to reveal secrets about your company, or it doesn't mean that you need to share a technique that you've perfected and you have a patent on, and you're trying to protect that. What it means is that you should not lie about something that has been done or not done. For example, a bridge collapses, you built it, the design was faulty because you forgot something in the design. You should not stand up and say the materials were faulty. That's unethical. To admit your faults, to admit your mistakes. So a lot of engineers, unfortunately, pull a politician on that. They say, to the best of my knowledge. And then these people have to come in and check to see if that's true and waste their time and energy and money. And it often happens that they're lying, unfortunately. There's a lot of money involved in engineering, not just billions of dollars, trillions, and even more of dollars, involved in engineering. And so people are very tempted to lie. Act for each employer or client as faithful agents or trustees. Notice that this is number 4. Number 3 is tell the truth. So even if your employer is going to be hurt, you need to tell the truth first, and then behave as act as a trustful faithful, I guess the word they use, a trustworthy and faithful agent for your employee. That also includes the fact that when you're working for an engineering firm, generally, you have a contract with them. And that contract usually says that something that you develop while you're working for us belongs to us. Or there's some kind of agreement where you own part of it, they own part of it, or something else. Most companies today are not that generous, quite honest. Most companies today say that while you're employed by us, you may not be employed by anyone else, including yourself. Any idea that you get is ours. End of story. And they can make a contract like that. There is nothing that says they can't. If you sign it, you're screwed. Anything that you develop during that time, anything that you develop that comes from something that you develop during that time, so any offshoots from it often are protected. And that's something that you need to be careful of. If you want to be an engineer who is developing new things and going out there and being the inventor, you probably should avoid signing a contract with a company unless you know exactly what it says, and it's very, very well stated. Avoid deceptive acts. Right? Don't try to pull the wool over somebody's eyes, because you're guaranteed when you're an engineer that you're going to meet 10 people a month that are smarter than you and cleverer than you, and they're going to figure out what you've done wrong. It's guaranteed. There are just too many smart people in these fields to try to fool, and it's not worth it anyway because it can lead to bigger problems. So avoid deceptive acts of all kinds. It doesn't mean that everybody needs to understand what you're doing as an engineer, because, frankly, you'll be lucky to meet 1 in 1,000 people in your life that understands what an engineer does. It doesn't mean you're being deceptive when you say, I really just can't explain that to you. It just means you just won't understand it, right? But you need to avoid trying to deceive people with your engineering or technical abilities. Conduct yourselves honorably, responsibly, ethically, and lawfully, so as to enhance the honor, reputation, and usefulness of the profession. These last 2 I like to talk about in terms of where we are now. We are now in school, where we're doing things for grades so that we can get on to the next course and we can get into a big school and we can get scholarships. And it's very, very tempting to cheat a little bit here, to deceive a little bit there, to get ahead a little bit just by doing some little thing. It's very tempting. Don't do it, because it will get you into a habit of doing that. and that will come back to bite you. Usually somewhere in your junior or senior year. Your junior or senior year, if you've had a just kind of a history of just cheating a little bit, copying homework off of an offline website that you found, or taking one of your professor's tests from another student so that you can study for the exam and get ace a test that maybe you didn't deserve to ace because you were reading off somebody else's exam as your study guide. Just things like that will lead to, in your junior or senior year, failure because you haven't done the things that you needed to do to grow as an engineer to get to the point in the junior year that you need to be at. Your courses in your junior and senior year would be the hardest courses. These courses just get harder and harder and harder in engineering. I'm not trying to scare you away, they just do. The great thing about it is that the teachers and the grading usually gets laxer and laxer and laxer. They become less and less worried about whether or not you're capable of doing the course and more worried about just teaching you the things they need to teach you. Because if you get to your junior year in engineering, you've already proven yourself, unless you've been cheating. Right? If you've been cheating, you haven't proven yourself, and you will fail in the junior year because you just won't be able to cut it. So do the hard stuff. You're going to struggle, you're going to fail every once in a while, but do the hard stuff, do it yourself, learn it yourself, and then when you get into your junior year and you get into that class where you take your first test and everybody gets like a 30% or below, and 30% is an A, you'll be happy with yourself. Hey, I got a 28%. That's like an A-, sweet. Okay? And you won't be getting the 4% that where the teacher walks up to you after class and says, you're just not cut. You're going to fail this class. You might consider recreation management. Okay? Avoid those deceptive acts and be an ethical person. Be an ethical person right now and choose to be that way. It's not something that is easy. Human beings are not naturally ethical. They're not naturally trustworthy. We're just not. From a very young age, children learn to lie because they learn that they get in trouble if they don't. Right? Learn that getting in trouble is better than losing opportunity or wasting opportunity. So, anyway, that is the code of ethics put out there by the National Society of Professional Engineers. Of course, like I said, there are other codes out there. We're not going to really get into them, but if you want to go and look up something about ethics in the particular field you're interested in, go right ahead. We're actually out of time, but I want to take a look at a couple of the things in the book. Actually, I'm not going to look at them in the book. I'm going to look at them online here. I'm going to look at engineering disasters. Right? You can go to Wikipedia or any number of websites, really, and you can learn about all kinds of engineering disasters. The I-35 West Mississippi River Bridge collapse in 2007. Okay? Let's see. Here we go. The Columbia disaster in 2003. That one, everybody knows about. But the first one, and that one was due to some, if you remember that one or don't remember that one was due to some tiles that came off of the Columbia Space Shuttle as it was re-entering the atmosphere. And they knew the tiles had come off. They checked that in space regularly. They knew they'd come off, but they had no mechanism for fixing it in space. I mean, they always came off. They came off all the time in space flight because the tiles are extremely delicate to mechanical failure. They're not built for being beat on and hit on and rattled. They're built to reflect, or to absorb, really. They're built to absorb heat. Well, they knew that they fell off every mission. They knew that too many had fallen off, and they had no mechanism for putting them back on in space. Now, they do, even though they're not using the space shuttles anymore. After that one, they figured out a method for doing that. They figured out a method for replacing those tiles while they're in space and making sure that those people were safe coming back in. Here we have one steamship way back in the 1800s, 1865. The steamboat SS Sultana exploded on the Mississippi River. 1,500 lives. right? That's all they've got here, but there are many, many others. A list of structural failures, maritime disasters, nuclear and radiation accidents. Many, many of these are due to engineering failures. And a lot of them are due to not following the rules of ethics for engineering. Okay? For example, the space shuttle, not the Columbia, but the first one that exploded, which was the Space Shuttle Challenger back in 1987 or 89 or something like this. The Space Shuttle Challenger exploded because engineers knew that there was a problem, and politicians and company leaders ignored them and tried to cover it up. So it wasn't even the engineers' fault, except that maybe the engineers should have gone to a higher place. They were afraid of losing their jobs. They were threatened with losing their jobs. And so they decided to they wrote their memos inside the department, and that's as far as they went. They said, we're going to leave it with them. It's their problem. Well, you know, the space shuttle exploded and people died, and maybe they should have gone further. Maybe they should have taken it to the press. Maybe they should have said NASA is launching space shuttles when it's too cold outside. And we've told them that, and they're ignoring us. You know, the president at the time was also involved. The White House was involved because they didn't want to have these space shuttle flights delayed. They wanted them to launch because it was good for politics. So you have all kinds of problems that you run into in engineering, political, economical, all kinds of things. Another classic one is the Kansas City Hyatt Regency. Let's take a look at that one really quick before we're done here. We're technically done in 10 seconds, I think. But we'll look at it really quick. Let's go back to the Hyatt Regency Hotel where was this? What did they say it was? Kansas City. So in Kansas City, Missouri, they built this hotel that had these walkways. These sky walkways or something like that. They don't show them before. They only show the after. But right here, they're showing what the engineering design was. The original engineering design had this rod, this steel rod that came down, and they had they essentially had these washers and plate nuts, these threaded plates that went underneath the walkway to hold the walkway up. Well, this was the design, and each one of these plates would have a force on it that was equal to essentially some fraction of the force that the walkway was exerting on it. The people building it decided they didn't want to use these long single bolts because they figured, well, a long bolt is really expensive, whereas some shorter bolts are much cheaper. So they used shorter bolts and took the first bolt down to here, and then the second bolt from here down. Well, it turns out just that little change, there were 3 of these walkways, I think, hanging from these bolts. That one little change actually increased the force on this bolt to double. And it was only designed to hold this. And a little bit more for just some safety factors. So what was the problem? The problem was it was designed by the engineer one way, and the builder built it another way, just figuring it would be okay. Well, it collapsed while they were having a party, and several hundred people were killed and injured. I don't remember how many it was, but it was a lot, a couple hundred at least. So, I mean, in that case, it wasn't the engineer's fault per se, but he probably should have been checking and inspecting, right? If it's his design and it's depending, and people's lives depend on it, and if I was the engineer, I would be there to check to make sure it was designed properly, it was built properly after I designed it, and nobody checked that. So, needless to say, these things are all well known by engineers, all these disasters, and so when engineers today are designing, they're thinking of these things in the back of their head all the time. The Tacoma Narrows Bridge is another great example. In the early part of the 20th century, they built this bridge across the Tacoma Narrows. I'm going to take just another minute of your time to show you this one. they built this bridge, and the wind in the Narrows started a vibration in the bridge. And at one point, the vibration got so bad that that's what it looked like, and you couldn't even drive across it anymore. Once it got that bad, it stayed that bad because all it needed was just a little bit of breeze to keep it going, and it got worse and worse. I mean, that's concrete bending there, concrete and steel that's bending like a rubber band. Here's another view of it. A couple of cars on it. Actually, there was a professor who was studying this bridge, an engineering professor. He drove his car out there and then decided to leave his car and walk off the bridge.
Yeah, didn't he run back on to try and get his dog or something?
Yeah, he did. Right here.
There we go.
Here you can see that he's walking along the middle of the bridge because, being a professor, he knows that there is some point in the wave that is not moving, and he found that was right in the middle of the bridge. So he walked in the middle because it was moving the very least. And then this is what happened after months of this vibration. It just failed. Just couldn't handle the stresses and strains anymore and totally collapsed. Now, can you imagine being an engineer building a bridge today? Do you think about these things? Absolutely. Not only do you think about this particular bridge in this particular situation, but you think about all the other situations that it could apply to. And so nowadays, when they build even big buildings, they think about the harmonics of the vibrations of the building. And so in the big buildings that are built today, usually in several spots along the height of the building, they will have entire, several floors dedicated to anti-vibration mechanisms. Usually there are huge pendulums or huge sliding blocks of depleted uranium or something extremely massive. So that as the building or the bridge tries to vibrate, these blocks take the vibration out, they dampen it out as they're allowed to slide back and forth or swing back and forth. I mean, it's the measures that they go to avoid this kind of mistake are extreme. At the top of a 50-story tall building, you can get vibrations that move the building as much as 15 feet, 20 feet. 50 stories is not even all that tall. I mean, the new one in New York is 100 something, the new one that replaced the Twin Towers. So, I mean, the engineering ethics are extremely important, and engineers take them seriously, at least the ones that are going to affect them directly. So, we will get into some more stuff in Chapter 5 coming up this week. We'll see you guys Monday. Have a good weekend. Good job on your bridges. You're welcome to use those materials again if you want, or to toss them out, or to put them up on your shelf or whatever. You can do whatever you want with them. I would recommend the plastic materials, if you use any of those plastic sticks, that you recycle those at the very least, and maybe even the dowels, because those are the more expensive pieces. The square pieces of wood aren't so expensive. So, anyway, have a good weekend.
See ya.
Remember your workbooks. Okay, and for the other one.